All right, so we are doing probability part 2. So these are the topics we'll be discussing, starting with discrete random variables and their probability distributions. So a discrete random variable, x, takes a fixed set of possible values with gaps in between. Here's the example of the probability distribution. Remember that every probability is a number between 0 and 1, and the sum of the probabilities is equal to 1 at all times. Here's an example of a discrete random variable. If we flip a coin 3 times and x equals the number of tails obtained, this is what the probability distribution would look like based on that purple box on the left. And we can check and see that the values of x are 0, 1, 2, and 3. There are gaps in between. The probabilities are all between 0 and 1, and their sum is equal to 1. Also, you can create a histogram to help you better understand your probability distribution. So for binomial distributions, the count x of successes in a binomial setting is a binomial random variable. The probability distribution of x is a binomial distribution, where n equals the number of trials of the chance process, and p equals the probability of successes on any one trial. The possible values of x are all whole numbers, and x equals the number of successes in n independent trials. When you're checking the binomial condition, check bins. This is bins. It's binary independent number and successes. Remember this. Okay, and this is our formula. So this is an example using the formula. Feel free to pause the video and try this one out. It's very helpful. To calculate the binomial coefficient and calculating the binomial probabilities, we wrote this out for you. This is on a TI-84 calculator. So a normal approximation for binomial distributions. What do you notice about these 3 graphs? You can probably tell by the title of this section, but as n increases, the data normalizes. Suppose that x is the binomial distribution with n trials and successes probability p. When n is large, the distribution of x is approximately normal with mean and standard deviation. So as a rule of thumb, np is greater than or equals to 10, and n of 1 minus p is greater than or equal to 10 is the normal approximation. So the expected number of successes and failures are both at least 10. So for geometric distributions, a geometric setting consists of repeated trials of the same chance process in which the probability p of successes is the same on each trial. And the goal is to count the number of trials it takes to get one success. So that's the difference between geometric and binomial. So here is our conditions we need to check. So binary independent trial successes. Okay, so a geometric random variable is the number of trials of y it takes to get a success in a geometric setting. The probability distribution of y is a geometric distribution with parameter p, the probability of successes on any trial. And those are some possible values of y. Here's our formula. And here are some examples of a geometric setting. Flipping a coin until you get heads, rolling a die until you get a 3, rolling a pair of die until you get doubles, etc. Here's how you would calculate a geometric probability on a TI-84. So part 4 is mean expected value and standard deviation of a random variable. So for binomial, the mean of a random variable is the long-run average value of the variable after many repetitions of the chance process. It is also known as the expected counts of a random variable. Here's how you calculate it. In other words, for geometric, the expected number of trials required to get the first success is 1 over p. If y is a geometric random variable with probability of success p on each trial, there's how you calculate it. So the standard deviation, the variance of a random variable, is the average square deviation of the values of a variable from the mean. The standard deviation is the square root of variance. Calculating variance is the equation above, and then calculating standard deviation is below. Remember that standard deviation remembers the typical distance of the values in the distribution from the mean. So linear transformations of a random variable. So when you add the same number a from each value of a random variable, it changes the measures of center of location, subtracts or adds a, but it does not change shape or measures of spread. You can draw it out to see. This makes it a lot clearer. Hence, so yeah, visualize the graphs or draw them out. When it comes to multiplying and dividing, however, these again affect measures of center and location by b, and it also affects spread, but again, it does not change the shape of the distribution. And here's an example drawn out, so you can take a look at that visually. If you want more to practice, feel free to Check out FRQ 2012 number 2. It's super helpful for these topics. And thank you so much for watching. I hope you enjoyed.